is the last of the background lectures covering what you either you know or don't know, but I'm sort of assuming that you should have known. So I'm just skipping quickly over these things, and this one deals with more networking issues. So let's start by talking about the load balancer. So when you have a server and it has a collection of users, then the server may not suffice for all the requests. And so you would have multiple servers supplying the same service. And you use something called a load balancer, which is just another computer, to distribute the request. And so as we'll see, the server registers with the load balancer when it's being initialized. The load balancer will monitor the health of the service and know which ones are healthy and which ones aren't. And the load balancer IP is the IP that's returned from the DNS server. So the client requests the URL of the server. The DNS server responds with the load balancer IP, and the load balancer distributes it again based on IP to its children. So let's look at a simple message sequence. So client makes a request gets to the load balancer chooses a server, and then the server sends it back to the client. So from the server's perspective, it gets an IP message. If you recall what the header of the IP is, it has a source and a destination. Well, the server is the destination, so it sends it back to the source. The destination IP is not the destination that the client had because the load balancer has changed it. So it changes the destination IP to get it to the server that's going to respond, but it doesn't change the source, and so then the reply goes directly back to the client. That's one model. A different model is that the origin can be changed as well. The source can be changed as well. In this case, the reply would go back to a load balancer or a proxy server, and it would then change the destination of the reply back to the original client so that the sender would get it. So you can play a lot of games with the sender and the recipient in the destination in terms of IP addresses to implement various types of policies, both for load balancing and for security purposes. And once it gets to the load balancer, there are a variety of algorithms that it uses to choose which instance. It could do round robin, just distribute the requests evenly. It could do a weighted round robin. Some servers may be faster than others, and so you would weight them by sending them more requests. It could do hashing, so the IP address of the source is hashed to determine which instance it gets. What this means is that if you get two requests from the same server, from the same client, it goes to the same server. This is not necessarily desirable from a reliability point of view. But these algorithms, from the load balancer's point of view, don't require knowledge of an instance load. That's a different process that we'll talk about in a minute. Now, suppose the load balancer becomes overloaded. Then you load balance the load balancer. So you could have a hierarchy of these things. So the IP address is going to be modified a bunch of times in this kind of situation. So a client sends a message, it goes to a gateway, which modifies the destination to send it to a load balancer, which modifies the destination to send it to a server. And then the response could go back to the gateway, or the response could go back directly to the client. Now, as the load grows, the client may become overloaded. So now we're back in the case where we have we need to allocate multiple servers, another servers, and auto-scaling is a mechanism for creating new instances. And this is based on a set of rules and on a monitor. So if you start with 3 servers, then they get overloaded, and then now we have 4, and this raises 3 issues. What makes the decision to add a new server? How does the new server get loaded with software? And how does the load balancer know about the new server? So making the decision is done by a monitor. So there's a separate monitor that looks at the CPU utilization of the various servers and has a bunch of rules that determines what action it could take. So if a server is at higher than 80% for 15 minutes, for example, then that may trigger the creation of a new server. If a server is below 20% for 15 minutes, that may trigger its deletion. The 15 minutes is an attempt to avoid particular spikes. So it could be that the machine utilization will be very heavy for some machines being backed up, for example, or some other kind of activity that adds load. And and so you want the rules to sort of wash out some of those effects. You don't want to allocate a new computer if it's not really needed, especially when you have a charging model that says once you have a new computer, you pay for an hour's worth of usage. Uh, but finding the right kind of algorithms is an active research area. So there are people that are studying the algorithms that these are used and trying to determine what the best ones are in various circumstances. And then the new server gets loaded with software based on something called a launch configuration. So there's a table someplace that the monitor knows about. When the monitor creates a new instance of the server, it it points it at the initialization at this table, and the table tells it what does load balancer to register with, what security groups it ought to be in, what machine image ought to be loaded, and all the types of things that are needed for initialization. And then the server, based on the information it gets, registers itself with the load balancer. So now let's talk about state. So they're going to talk about four kinds of state: session state, client-side state, server-side, and persistent state. And so let's start by talking about a session. So historically, a session used to refer to a series of interactions between one client login and the termination of that login, whether you log out or you time out. These days, a session can also span multiple logins, so you have the notion of, in Netflix, of I'm looking at a video, I stop watching the video, log on to a different, I log on again, maybe from a different machine, and I pick up the video from where I was. So that's kind of an expanded notion of session, but we'll deal with the session of a single login. And so what happens when you log in is that to a service, the service gives you a code that identifies you. It's called your session ID. And you have other information. And this is both for performance and security reasons. You have other information that can be included, such as your physical computer address, and that's part of the security information in terms of the man-in-the-middle attack. Man-in-the-middle is somebody who's listening to your session and pretending to be you. And these kinds of things are typically managed by your browser on the client side. If state is saved on the client side, then with each request, the server has to know all the information, right? All the state that's been saved. And so that requires network overhead. It also means that data is stored on the client machine, and this can have both security implications and reliability implications. If your services are stateful, that is that the services themselves store state, then that has several implications, one of which is that it makes scalability more difficult, because if your service is stateless, then you can add a new service, and the load balancer doesn't have to worry about which service it sends a request to. Their services are all the same from a state point of view. And if the server in fact stores state, then you have to be more careful from a load balancer's point of view. Now, and we'll get into this, there are tools that enable you to share state across multiple servers in an efficient way. And so you could have stateful services where the state is shared. And so the services themselves are stateless, but the provisioning of the state, the supplying of the state is done in not over the network, but well, it is over the network, but in a different fashion, not as part of the HTTP protocol. So state can be kept either in the service or in some persistent store. That's the state that the client doesn't have. And the choice depends on the volume of data, the latency involved, the synchronization needs, and the time the state's expected to persist. So if it's going to last a long time, then you want to put it in persistent storage. If it's transient type of state, then you might keep it in a shared cache, something like memcache. So when you're making these decisions as a designer, one of the things you should know is just how long does it take to access relevant pieces different ways, and these numbers change with the technology. But the thing to keep in mind is if you're getting something from the Europe, for example, it's going to take orders of magnitude more than if you had it in memory. If you're getting things from a disk, then you have the time involved in seeking plus the time involved in reading. If you're getting things from a solid state device, then you don't have the time in seeking, and the time in reading is faster, and so on. So again, not the particular numbers, but the orders of magnitude are important. So, and this just elaborates what I said. One of the things that's typically done with persistent storage is that it's replicated. So it's replicated across, you don't know, we haven't talked about regions and availability zones, but it's replicated geographically into different data centers. And so that takes time. And it makes keeping data consistent across different occurrences more difficult. And again, we'll talk about some tools later. Okay, so the secure shell. This is a standard protocol and the software that does it that enables you to control one computer from another. You do an SSH login, and it looks like you're on that machine. So SSH has a concept of known addresses, which you'll see in the exercises, and it allows you to log in without providing a password. Most of the tools that we'll see in this semester use SSH either explicitly or implicitly. And SSH is based on an algorithm called the Diffie-Hellman algorithm that dates from, I'm thinking, mid-70s, maybe a little bit later. And so this is an algorithm that enables you to publicly disclose most of the elements of an encryption scheme. And the PNP decoding assumption says that this problem is NP hard, so it's a difficult problem to solve. And it provides the Diffie-Hellman algorithm provides a method for generating a shared secret between two people over an open channel. So you have eavesdroppers, and you want to avoid them from knowing the secret, even though you're talking about you're talking about the shared secret and creating the shared secret over this open channel. And there's a book that's on the net, Crypto 101, that talks about some of these crypto algorithms. So most encryption algorithms are based on, well, I shouldn't say it that way. We'll get into encryption algorithms, and there are single key and multiple key types of encryption algorithms. The single key says I have a key, I use it to encrypt, and I use it to decrypt. And that's less secure because over time somebody could conceivably break that key. So if you've ever read any spy books, you've read about the one-time pass word that you would use it once and then you would throw it away, so somebody can't break it. That's the single key type of thing. Somebody would use the key to to encrypt, and then somebody else would use the same key to decrypt. When you're using multiple keys, think of the public key infrastructure, private keys, then it starts by saying that we have a large prime number, which turns out to be relatively easy to find. That was kind of a surprise to me. And then you have a base such that this base raised to this prime is 0. So I have from years ago, I had a friend that was a number theorist in mathematics, and he said the nice thing about number theory was that there were absolutely no practical assumptions. That was in the 60s. Life has moved on, and there are a lot of practical assumptions of number theory. And one is, how do you calculate these things, like raising something to a large prime and making sure it's 0. So computing y equal g to the x, where g is this base, modulo this large prime is easy. But finding x when you have all the other factors is difficult. So you can make y, g, and p all public without compromising the ability to find x. That's the essence of the Diffie-Hellman algorithm. And so what happens is you have two people, Alice and Bob, who are standard protagonists in the security world, and they select P and G, and these can be publicly shared. And then they select random numbers, large random numbers, which they keep secret from each other, from everybody else. And then Alice computes a number based on her secret number and sends it to Bob. Bob computes a number based on his secret number and sends it to Alice. And then it turns out that the exponents are commutative, and so they can both arrive at the same secret, but the eavesdropper can't, because the two numbers that Alice and Bob use are kept secret. So this enables them to share a secret. Now, how does this work with SSH? Well, let's get back to SSH. And so what happens is that machine A and machine B use the Diffie-Hellman algorithm to establish a secure connection. And then they use to create a one-time password. So they, in fact, do this single use password one time for the session. And they use it both to encrypt and decrypt, because it's more efficient to do that than it is to have two passwords, a public key and the private key. And this one-time password lives for the life of the session. So just to summarize this, load balancers manage multiple servers for a single service. How state is managed is important. SSH is a standard technique for controlling remote computers. It uses the Diffie-Hellman algorithm. And scaling is a matter of adding or deleting resources.